Shane from the Qatar University, and the title is Water Energy Access Technology to Mitigate Climate Change. And Dr. Shane or Professor Shane or Dom Han, he used to call Shane himself, is a research associate professor at the Center for Advanced Materials, and he joined and also joined associate professor in the Department of Chemical Engineering at Qatar University. He received a PhD from Texas A&M University College Station in 2009. He has over 20 years of experience in development of water, environment, and energy technology using nanomaterials and environmental, physical, and chemical technologies such as adsorption, membrane separation, photoelectrochemistry, and advanced oxidation processes. Until now, his research has been supported by National Research Foundation of Korea, U.S. Department of Energy, U.S. Geological Survey, and Qatar National Research Fund. The title of his presentation is Water Energy Nexus Technology to Mitigate Climate Change. I welcome Professor Shen. He is our colleague and very interesting, working in interesting area, and he is a expert in this area. So I welcome Professor Shane from Susan. The floor is yours. Please.
The speaker, including Dr. Aniko, Sean, Chen, and Ephraim. So it's my last turn to introduce my ongoing project regarding the water energy nexus technology contribute to mitigating climate change. So before starting, I want to introduce what is the water energy nexus. Nexus means co-interdependence. So that means water energy highly correlate. For example, to get the purified water from water resource, we need to put energy because the all water contains a lot of salt, making the water have a certain level of salinity. So to get only water molecule from that salinated water, we need to put work energy by chemically or thermally and electrochemically and physically, sometimes using membrane or the membrane distillation. Many our previous talk about this topic. And the other hand, to get the produce energy, we need to require some water. For example, cooling water in the industry activities, and sometimes the GTL, the industry requires some water to refine the fuel or extract the fuel from natural gas and oil. So like this, water and we can say water and energy, highly correlate. So World Bank defined another terminology, water energy nexus. They use this term, thirsty energy. So energy always thirsty. They require the water. So this slide shows the one of a good example water energy nexus in Qatar. Recently, 4 or 5 years ago, Qatar, installed the Hollow power and desalination plant. They had 3 blocks. So this block is for the power block. They use the natural gas-based power plant, and this one is water block. They use in summer MSF, and this one water block, another water block using membrane-based reverse osmosis. So in the power block, they use natural gas, I already said, and they use the gas turbine. So they the fire and getting the heat, the energy from the natural gas. Finally, they release some CO gas and some heat, still water. H2O with nitrogen gas. So, but this H2O has very heat, and there is some basis on thermal energy resource. That energy, this is the steam is connected to the boiler and can provide heat energy to distillate the seawater to get the purified water, and the generated the electricity power can be used energy consumption of reverse osmosis. So that is a good example of water energy nest. The power plant provide, heat energy and electrical energy for two different types of thermal and reverse osmosis to get the, clean water from seawater. So finally, we have also achievement this kind of the Qatar Hollow power plant and desalination plant. The 20, the megawatt power, capacity, and they produce more than 130 million gallon water per day, and they, cover the 30% state of electricity need and 40% water needs. And this plant is one of the largest in this country, and also recently the SWR process is 10 more to utilize the remaining the electric power in the winter season. So we to properly utilize all electricity produced in Umhalu power plant. So even with successful installment and operation of this Umhalu hybrid process, we cannot avoid generating CO2. Mostly the natural gas based power plant that release a lot of the CO2. So in the bottom, the diagram shows the history of the CO2 emission in Qatar from the 1972 recent years. From the 2000, the CO2 emission is gradually decreased, but still highest in the world compared to other countries, including UAE, Oman, Kuwait, Iran. So yeah, even in the other countries in the world. So that is this other advantage case the water energy in a plant in Qatar. So we need to consider climate change. The CO2, as you know well, contribute to many global warming, finally leading to bad case of climate change in the world. So how to manage water to contribute to climate change mitigation like this? Seawater desalination sector. So we need to our best to reduce energy consumption. Otherwise, we need to develop high advanced membrane to get the anti-fouling. So if you have many severe fouling quickly in the outer membrane, they lead to more energy consumption. So many researcher and industry still to their best to make the best of the anti-fouling membrane using nanotechnology. Other best way, SWR process, cover only the pre-treatment and seawater desalination outer process and post-treatment. That has large scale plant, so we need to optimize all together to minimize the energy consumption. So that can contribute to the CO2 mitigation as well. And in the wastewater treatment, yeah, of course, we need to our best to reuse the released water and waste use. And also we need to develop a technology to valorize the waste stuffs in water. So for example, Dr. Sean introduced this technology. We can recover the nitrogen and phosphorus wastewater, even in urine, like the previous wastewater. So we also do our best to reduce also water consumption in our life. And the other sector for minimizing climate change is we can develop some other energy economy like hydrogen economy, and also like the airplane explained a lot blue energy using the salinity gradient technology. And otherwise, we need to maximize using the brine that leads to some other, the water projection plant, including SWR process. Otherwise, to maximize the utilization of this. So here I focus on seawater desalination and renewable energy from water. First, I want to talk about in seawater desalination. 15 December, the COP21 is initiate the global clean water desalination alliance addressing the H2O with the CO2. This diagram shows water production using different technology with various energy resource. When we use nuclear, the CO2 emission is very least compared to the other case. Whatever we apply the energy source for desalination plant, mostly the SWRO process the least the amount of CO2 atmosphere compared to other thermal desalination plant like MED and MSF. MSF case is the largest CO2 emission. But still, when you use, Dr. Efron already addressed energy consumption level of when you use the SWR process, mostly the 2 or 3.5 kilowatt hour cubic meter, but still high. So many, this energy consumption, more than 90% is focused on the operating high vacuum the pressure pumping. This is highly related to the feed water quality and concentration level. So Middle East country salinity is higher than other country. The osmotic pressure is around 38 bar. And also in Qatar, Halu SWR plant use water recovery of 45, so that we can have the like 1.8 times salinity higher than the seawater. So overall, so high vacuum recovered these two the osmotic pressure. So if we manage well this feed water quality and concentrate the salinity level, we can minimize the use of electricity in SWR process. So how can you do that? So to reduce the salinity feed, mostly F4 process can be combined to down the salinity of the seawater. But this case, we need another water stream. So it is good for the SWR process, very near to, close to the like wastewater treatment plant. So how about the concentrate? To manage the concentrate out of brine, so we need this, out of brine, the osmotic pressure around like mostly the 50 bar. So it's a high osmotic energy. We developed some recovery the process like pressure retarded osmosis or reverse electrodialysis. We can harvest the osmotic energy and can be used for again SWR operation. So also Dr. Ephraim explained the energy recovery device. We use this concentrate, the osmotic energy with the seawater. The generating mechanism, help to provide the additional energy through the booster pump, so that 30 years ago, SWR released they consumed a lot of energy, but that invent of energy recovery device can save the more than 35 energy consumption in SWR process. So this slide, I want to start explaining of how water itself can be used as source of the energy carrier. Yeah? So if we can develop the water for generating green hydrogen or blue energy, maybe the system can guarantee the least CO2 emission involve the process. So as you know well, green hydrogen can be generated from general technology of electrochemical water splitting, and blue energy, we can use the two different water stream having a two different level of salinity gradient. So let's talk first H2 production by water splitting in seawater. So when I saw in Google image, when I talking about the general hydrogen green energy, I found this slide. So our list in 1974, he made history with the title of Mysterious Island. He addressed the water as pure. In the context, he said, water will be the carbon of the future. So water, molecule is H2O. There is no carbon component element, but he believed in 1974 carbon can be energy in the future. He's smart. So our one MQNRF project suggests using the saline brine to trigger the hydrogen production using a photoelectrochemical system. So we consist of 3 compartments. Middle chamber is the source of the saline water. When you illuminate the sunlight, the photosemiconductor starting provide electron. So that cathode drive the transport of sodium. Finally, they can increase the conductivity. So more hydrogen can produce. So as you know well, in the anode system, they are make more oxidation chemical reaction. So chloride ions move from this desalination chamber can be involved with the production of a reactive chlorine species. So there is one of the hydroxant that can have power to degrade some organic including wastewater. So 3 compartments involve the different 3 chemical reaction: wastewater treatment and desalination. Here is molecular hydrogen production. So this is one of the examples for experiment results we obtained. So over time, until 12 hours, the hydrogen produced linearly up to the 24 micrometer. This, the almost more than 90, efficiency. And also in anode chamber, ammonia is, urea is the model compound of the wastewater. Quickly the degrade with some intermediate like the ammonia and nitrate. Nitrate is gradually increased all over time. So that is successful proof of concept for 3 diverse chemical reactions using this chamber. And I want to talk about now fluid energy. Dr. Efren already explained a lot of the R&D process. And mostly people are focusing on solar energy, wind energy as one of the renewable energy. But if we properly manage the salinity level in the 2 different water streams, we can generate the fluid energy. So those are widely the highlight and studied a lot recently. So this the electrodialysis uses the salinity gradient power that can be obtained by exploring the Gibbs-free energy available in the mixing 2 aqueous solution with different salt contents. So it will cover the 2.4 to 2.6 terawatt as a potential. And when you use the this blue energy, maybe we minimize releasing the greenhouse gas like CO2, CH4, and 2O. So there is a potential for us to use the reverse osmosis to generate blue energy. So Qatar, has a lot of the industry side related to energy production. Also, they have, a lot of the water stream having a different level of salinity. For example, produced water, cooling water, low salinity wastewater, and brine seawater. So if we use coupled well matching the good salinity difference in the RED stack, we can generate what you want, power density with the appropriate voltage that required for some combined chemical process or other process like a urine chemical recovery or CO2 conversion process or hydrogen production using electrochemical system. So I skipped the basic principle that the Efraim already explained in detail about the operation of the RED. So another my QRF project utilized using the reverse electrolysis combined electrochemical system to convert the CO2 into the another chemical reaction like a formate. So SWROT cell plant has released out of line. So we can take the out of line with wastewater stream. The RED can generate the power. The power can be used for operation of subsequent electrochemical reactor for CO2 conversion. So first, ROD operate by considering several experiment or operating conditions like salinity level and different applied resistance and number of cell membrane pairs and also different solution flow rate. So when it picks the high concentration level with one more NaCl, we choose the different level of the low concentration with ammonia sulfate. So when we have lost the concentration, that means we have high salinity gradient difference that they can generate the most highest power density around the 2, and we have around the 1.2 voltage. When we increase the flow rate, we can get more the power density the value. So the faster flow rate, minimize the loss of the salinity gradient. And when you increase the membrane number pairs, of course, they can generate more power compared to a low amount of membrane cells. So that kind of RED can combine the subsequent electrochemical system. Yeah. So in this CO2 electrochemical system, we compute similar over the hydrogen production using the desalination chamber embedded electrochemical system. So so also we more developed in the desalination chamber, like RED process. We applied the alternated ion exchanging membrane over cation exchanging membrane and anion exchanging membrane. So they can contribute to the good least use of energy consumption. When you see data, so when you increase the desalination chamber stack, so when you compare it the least amount, we save a lot of energy consumption, and the more increase the desalination chamber and get good desalination rate. And also we applied different types of the experimental conditions in each chamber from case A, C, and mostly the case C has good current density training, so more high activity of chemical reactions. So over time, within 1 day, we can get gradual increase formate. The Faraday efficiency reached more than 90% use. Okay, so this is good result when you use the this multi-stack desalination chamber embedded electrochemical system. So we are now trying to combine two systems so we can know. So for the operate the CO2 electrochemical system, we need 1 and 2 voltage of overpotential. So that is based on our previous experiment. Yeah, so the 5 member state enough to produce the 1 volt level voltage. So now I want to talk about the more inversion of food inside the water energy nexus technology under air pollution condition. So also air pollution, the worst our condition, such as our human immunity. So we suggest our Q&A project is suggest using the electrochemical combined EPO process, to utilize the sulfur containing gas released from industrial activities. Mostly the industry tried their best, to capture this kind of the air pollutant, but in this system, we want to maximize the use for electrolyte in this electrochemical system. And this, sulfuric gas is well dissolved in ammonia containing solution. So we found the ammonia sulfide or sulfate is to electrolyte generate the hydrogen in the developed configured in electrochemical system, and that solution will be circulate, recycled to following the port osmosis can be used for draw solution when it get combined over the seawater feed solution. The solution can be diluted, and without any the draw solution recovery, we can directly use the agriculture application. So when we finished this project, they reached the TRL 4. So this is actually the schematic of experimental setup for PC combined fertilized through port osmosis. This is P system, and this is fertilized through Apple system. So this data is for photosynthesis, this data for the electrochemical system. So good performance criteria is FDF process is getting a higher value of water flux and water recovery. So 3 cases would be candidate good condition when you use different ratio of the ammonia sulfide sulfate. So with a similar condition with a different level ratio, in the P system, we get certain result. We found which one is better, and when you consider 2 cases, we increase the each individual concentration ammonia sulfide sulfate with a specific ratio, and we test together in the hydrogen evolution in PC system. So we reach what is the good condition, but we cannot say which one is the best over there. So we are focusing on more water flux recovery. Maybe this case would be better. Consider the PC result. So with this optimized result, we applied to see growth of the plant in the basin. So we applied it to 3 months. When it also we compared it to use of municipal water. This FDS is fertilized the draw solution. So finally, when it count leaf and stem high within 3 months, mostly the FDS intake the plant will grow up well. So finally, I want to conclude with this slide. I already mentioned 3 sectors. So important point at current stage with the current technology level, what we can do our best to mitigate the CO2 release is at lowering the energy consumption, so we can get sustainable our environment, but we are failed to manage the energy consumption, so we can lead it to high CO2 emission into atmosphere. I thank for all finance support to the Qatar University WTO PwC Capricorn Shell Axiona, and I very appreciate my research group for their hard working to get this research, and with our international collaborator, Professor Hyunung Park and Dr. Sean Chen, Rory Koshio, Kakushima's Evashir, including all of our internal Qatar University collaborators. Thank you very much for your attention. I